This is the agave palmeri. This majestic desert species spends years growing its huge, spiky rosette of fleshy leaves. When it finally matures, sometimes after several decades, it grows a single long stalk laden with flowers, which produce seeds, and then it dies. This is the Pacific salmon. After spending its childhood years in the ocean, the adult fish will return to the river, swim against the current, jump up waterfalls, celebrate the end of their journey with a big ol' sex party, lay their eggs, and die. This is a mayfly. Contrary to popular belief, it does not live for a single day. In fact, most mayflies have lifespans of at least a year. But, oh yes, when baby mayfly is all grown up and ready to get its wings, then boom, have sex, lay eggs, dead within a week. Octopuses die after reproducing. So does the male Antechinus, so do a large variety of insects, and so do most of humanity's favorite food plants. If we step back and think about this for a moment, the question that comes to mind is, why? As in, why don't we all do that? Why do bears and trees and ground beetles and friggin' humans insist on reproducing multiple times in their lives? Why can't we all aspire to the awesome reproductive explosion of the agave? Oh, is that not your question? Okay. Let's do a thought experiment. Let's say there are two organisms, A and B, competing for resources. Let's also assume they can reproduce without sex. This doesn't actually affect our conclusions, it just makes things easier. Each starts with 10 adult individuals. Over the course of a year, A will gather 5 resource units. 4 of them will go toward reproduction, but if it wants to see another breeding season, it needs to spend the last 20% on itself, repairing and maintaining its body, surviving the winter, that sort of thing. So, at the end of our first breeding season, we will have 10 adults, each of which having produced 4 babies. Okay? Okay. Next, let's say reproductive maturity takes 1 year, and 30% of all individuals survive the winter. That means we start the next reproductive season with 12 new adults, plus the 3 that survived from last year, and again, everyone gets 4 babies each, so this year's reproductive output is 60 babies. Third year, about 20 adults, 90 offspring. The total population at this point is more than 100 and rising. This is going pretty well. Let's leave A for a moment. Now, organism B doesn't mess around. Every ounce of resource gathered is going into making babies. That means 5 offspring per adult, where A could only muster 4. And again, 30% of those offspring survive to the next breeding season, but this time, because all energy went into reproduction, there are no surviving adults from last year. Organism B starts from scratch with every generation. This is known as semelparity, although sometimes biologists will use the more cheerful term Big Bang reproduction. A's lifestyle, saving some energy to reproduce again later, is called iteroparity. Okay, so how does B compare? Well, at the start of the second breeding season, the strategies appear evenly matched, 15 individuals each. But in B's case, the extra reproductive output pays off. When population A breaks 200 individuals in year 5, population B is already at 300. Year after year, even as A grows exponentially, B is always one step ahead. In fact, it doesn't matter how unrealistically small we make the cost of surviving after breeding. It doesn't even matter how long A can extend its lifespan. Even if A makes 999 offspring to B's 1,000 offspring, and nobody ever dies from anything other than reproduction, making that one extra baby and dying is still better than iteroparity. The coolest questions in science are the ones that change while you're trying to answer them. In this case, the question, why are some species semelparous, becomes why aren't all species semelparous, given that simple math shows it's a superior strategy. This is Cole's paradox, after Lamont Cole, who asked precisely this question in a landmark paper in 1954. In the same paper, Cole also went on to suggest an answer. The model we've built here is very simple, but we actually only need to change one of our assumptions to get a different result: mortality. So far, we've assumed that mortality due to external factors is the same for adults and juveniles alike, 70% per year, but this isn't necessarily going to be the case in nature. Adult individuals are larger, stronger, have more experience, they might be less likely to be eaten, or less likely to freeze on a cold night. What happens if first-year survival stays the same, but now adults have a pretty decent chance, let's say 50%, of making it into their second year? This time, A starts the second year with an extra 2 reproductive adults. At first, this doesn't seem to matter. B still puts out more babies per adult and comes out on top. But in the third year, A's supply of surviving adults is starting to make itself known. 8 years in, population A is twice the size of population B. Similarity is no longer king. Of course, sooner or later, adults of pretty much any species are going to die of old age, but the point has been made. When adults have better extrinsic survival odds than juveniles, investing in intrinsic adult survival becomes worth it. Conversely, self-destructive Big Bang reproduction should evolve in species that live under stressful conditions or high predation, where reproductive adults are pretty likely to die soon anyway. The field of biology that studies how organisms use their resources, how often and how much they reproduce, how early they mature, etc., is called life history theory. It can be used to tackle some very fundamental questions like why some creatures are big and some are small, or why some live for weeks while others live for centuries. Life history theory can get fiendishly complicated, but like with Cole's paradox, a lot of it comes down to risk management. If you're interested in life history theory, leave a comment. I might just make more videos on it sometime.